All right, this is third class on functions. Today is when the rubber hits the road. So you know what all of these functions should look like. It's just now what is the equation and what is the regression, because you're going to be given a bunch of data that you'll see as we go through this. And that data is going to be it's going to follow one of these particular functions. So lines, you know a line is positive slope or negative slope. And the basic equation is y equals mx plus b. The regression equation, much like you did with trig, will be y1 tilde mx1 plus b. And then when you do this, the Desmos will give you an m value and a b value. It'll give you an r squared value as well. And remember, the r squared value, the closer to 1 that is, the better the data fits the shape. So you'll see in a minute, if you get a bunch of data that looks like a line, you'll use this. Parabolas, open up or open down. The equation of a parabola is y equals ax squared plus bx plus c. The regression curve is y1 tilde ax1 squared plus bx1 plus c. And then again, you'll get an a, b, and a c value and an r squared value out of that. Cubic has this look or this look, and it's y equals ax cubed plus bx squared plus cx plus d. And it's a little bit bigger, but same look. y1 equal or tilde ax1 cubed plus bx1 squared plus cx1 plus d. And you'll be given an a, b, c, and a d value, and an r squared. And basically, those letters, those constant values will go in place for those those coefficients or constants. And exponential growth, that's what we did last day. It, remember, looks like this, has a horizontal asymptote there. Looks like this, gets closer and closer to 0 on this side, has that look to it. Basic equation is y equals a bracket b raised to the x power. In regression form, that's y1 tilde a bracket b raised to the x1. And in this case, you'll have an a and a b only, and an r squared again as usual. Exponential decay, just knowing that it goes down towards the asymptote this way. Same equation, really. Just what'll happen up here, you won't, for the growth, the base will be bigger than 1, so because it'll be growing. For this one here, the base will be between 1 and 0, like a fraction or a decimal, like a half or a third or 0.2. And it has the same formula like this. It'll have an a and a b and an r squared. Just this b value here is going to be between 0 and 1. This b value here between or bigger than 1. Log growth. Just give me a sec here. Log growth, I know logs look like this. I'm just going to double check real quick, because sometimes I'm looking at an answer key at the back here. Yeah, okay. So they're going to have it in that form. Just let me double, yeah. Okay, just want to make sure it was on the right. So they're going to have it in this form, b plus a log x. It's just a matter of how you write that. Sometimes I put the a log x first and then the b, but just looking at the answer key so you don't get confused, it'll look like that. y1 tilde b plus a log x. And again, you'll have an a and a b. Okay. And logarithmic decay just goes the other direction. it has the exact same formula. The only difference is the A value here will be positive, because that'll give you your growth. This one here will be negative. And you won't even care about that. It'll just happen. And you'll again have an R squared for both. And then sinusoidal you've done already. You know sinusoidal has this look to it. And that's y equals a sine b bracket x minus c, close the bracket, double bracket, plus d. That one's old hat from our last unit. That one you're used to. x1 minus c, close the bracket, plus d. This doesn't quite fit on the page. Okay, so these you just have to have on your summary sheet, and you're allowed to have those written out. You just have to know what shape you're intending to look at when you do this. So, as I flip the page, this is just a small little example, which we're going to go through together. I'll get my phone out so you can see it right on the screen. Is, let's say you're given a bunch of data, and you plot the data, which is these dots here. You would look at that data and say, what is that? Like, is that a line? Is it a quadratic? Is it a cubic? In this case, it's a quadratic. So then you would type in your regression quadratic, which is right there, just stolen right from the front page. You'd get an A, B, and a C. And then there's your R squared. It's 0.9963, so it's really close to 1. So this is a pretty good curve. And then you would end up using this curve to interpolate or extrapolate. And that just means, interpolate would mean you're finding data within your curve. Extrapolate means you would predict the future or look in the past. You would look what's going to happen based upon the curve, just like you did for your sinusoidal. So we'll do some examples to go through that. So now, this is again, so where the rubber hits the road, this is the fun part about science right here, because you're going to be given data of a certain experiment. Sometimes there's no meaning to the experiment. Sometimes there is complete meaning to the experiment. Like this one, again, this would be an important thing for a medical situation, or even for RCMP when they do blood alcohol tests and all that kind of fun stuff. So concentration in milligrams per liter of a medication in a patient's blood is measured as time passes. Susan collected the following data and has attempted to express the concentration as a polynomial function. So again, that's kind of a little bit of a hint. Polynomial function, it's either going to be a line, a quadratic, a cubic. We'll find out. When I look at the data here, I might be able to kind of make the gist of what's happening, but a picture's worth 1,000 words. So you're going to go to your phone. I'm just going to grab my phone. See what's going on here. Okay, here's my phone. Go to Desmos. Where is little Desmos? So I can see it better. Maybe I can't. I don't know. Let's see. Okay, I'm going to enter the data. So that, again, that's old hat to you. You know how to enter data. So I'm going to go to the plus sign, table. Again, bear with me. This is slow. 0. I would do it along with me. See if you can beat me, actually. Probably can. Will I bugger up? I don't know. We'll see. We'll see. 7.59. Good for it. Y1 or Y is 0. 26.9. 41.2. Oh, buggered up there. 41.2. 47.8. 46.0. I don't need the 0, but I put it in for good faith. 36.8 and 20.3. Before you walk away, double check to make sure you've entered everything correctly, because nothing worse than doing all this and then typed in a wrong number, just like a goob. So here we go. Now again, I'm expecting to see a bunch of dots up here, but notice I don't see that information because I don't have the right scale. So again, I go to the wrench. I love the wrench. I can see my x is big as 9, low as 0, so x is going to go, I don't know, -2 to 10. That sounds good. My y, it goes as big as 47, so I'm going to make it at least 50, and maybe -2 to 50. Let's do it. Then I'll start seeing my dots, and then I would then at that point I would play, and then at that point, to me, it's pretty obvious. I see all my dots. That to me looks like a parabola, quadratic. So right away, I am going down to here. I'm flipping over to my quadratic formula, or quadratic regression, I should say, and I'll type in y1 tilde. It's easier on a keyboard, but that's okay. You have to do it this way too, so I'll suffer with you. x1, don't forget the 1, that'll mess with your head, plus b x1 plus c. There she be. Okay, so there's my data. Type that in, then all of a sudden I get a nice little curve going through there. Look at my R value, pretty close to 0. Done like dinner. And now I can use this to answer questions. So first question is, it says perform a regression to determine the model of this for this data and state the equation. Well, we just did that. I'm just going to literally copy this right here. So you can do it two ways. You could do it this way. I'll do it this. I prefer this way personally. I just write out the general formula, and then I list out the A, the B, sorry, it's out of order here, 18.7643, the C, and sometimes I write down the R squared because it makes me feel good. So there she be. Done. Over. At that point, again, the second way to write that is to, sometimes people write this, they actually put the A in front, they put the B in front, they put the C in front. You'll notice in some of the future answer keys, they just throw it right in front. There it is. Good for it. Okay. Now, we're going to look at this picture. Use the model to predict the concentration when time is 9.5. Well, time, I can see here is the x, so this would be x equals 9.5. So I go over here. I'm going to go down below my curve there. I'm going to go x equals 9.5. And 9.5 is just a little bit beyond the actual data because it only goes to 9. So right away I know it's extrapolation. It's outside the data. It's bigger than 9. If it was between 9 and 0, that would be interpolation. This is outside it, extrapolation. And then I can click on where that hits. Click. I'll write down the point just to make myself feel good, and then I'll disclose what this means. So this represents how many hours? At 9.5 hours, you have 11.7246, and that's the Y value. And what are the units for Y? Y is concentration. It is milligrams per liter. So that's how many milligrams per liter that person would have in their system according to this model. Good. Next one. Use the model to predict the concentration when time is 5. Well, it's the same thing. So 5 hours. 5 is within the time frame, so that's going to be interpolation, enter. And then literally I will do the exact same thing. Go here, change this to a 5, save myself some time. Click on it. 5 hours and 48.56746, and that's going to be in same units, milligrams per liter. Now, I'm not a doctor. I don't know what this medication is. Maybe this is really good for the person. Maybe it's bad for them. I don't know. Or maybe if it goes too low, people that have diabetes, they have to worry about things like this all the time with their insulin and stuff. Very practical. Use the model to determine the time when the concentration is 10 milligrams per liter. So when I look at that, that is the Y value. The Y value is 10. So again, that just screams, get rid of the X, put in Y equals 10. Boom. Good. Oh, there's two of them. Interesting. So because it's a parabola, it actually hit twice, here and here. So I have to write down both of those pieces, 0.49221, comma 10 and 9.603, comma 10. And there's two values. So what was the question? Determine the time. So that time times our 0.49221 hours and 9.603 hours. So I guess what's happening, the person takes the medication, their blood concentration goes up, hits that point, then it goes higher, then as it's coming down, as it's not in their system, they're peeing it out or excreting it out or sweating it out, whatever happens. Kidney function, all that kind of stuff uses it, it's down to 10. Good. Next guy. Now, what I'm going to do here is, all of this is the same stuff. It's just the main piece here is basically, are you able to type in this data, look at what it is, a line, parabola, cubic, and so on. Determine what it is. Sometimes you can, there's two choices. Sometimes the data might suggest two values, so you could go with both, but that's not always the case. So let's just go through this guy here. Same clue, same idea, clear out all the mess, same jazz. Again, hardest part for me, typing in all this crap, especially look at that, messing up already. 3. Now it goes up by 1, 4, 5, 6, 7, 8, 9, 10, 11. I just want to make sure so I can take advantage of the program's pattern recognition. This, 2, 4, 8. I can see a pattern here right now, but it's not, Desmos isn't doing it for me. 64, 128, 256. I can see it's doubling. Just the way the numbers are working out, they're exact. Okay. Now I look at that graph. Again, I'm going to get the right window because right now I'm missing some points up here. So I'm going to make sure X goes at least to 11. Right now it's going to 17. That's fine. But my Y should go at least to 2048. So I'm going to make it go 2100. And there's my picture. And it's pretty obvious what that is. Exponential growth. So I might even, I'll just be like, boop, exponential growth. Formula, y1 tilde a b x to the first, x1. There's my equation, y1 a b x to the 1. Go and type in y tilde, someone's honking, a bracket, b, close the bracket, raised to power of x1. Oh, don't forget the y1. If you don't see the connecting of the dots, you've missed the y1. And look at this guy. A is exactly 1, B is exactly 2, and R squared is exactly 1. That just means this is like an exact fit. Exact fit. So that's done. And notice the base is 2 because the data is doubling. Not a surprise. How many bacteria after 17 hours? Hours is X. Plug in X equals 17. And now here's where I got to be careful, because notice 17 is way over here. The graph grows so quickly, it's way up here. So I'm going to have to fart around with this window. It's probably going to be big numbers, so I'm going to have to play around with it. I might use my fingers, but I don't feel like it. I'm just going to go with this. I'm going to go with, like, let's say 40,000. Let's go 400,000. Is that enough? Yep, 400,000. Look at that. That's enough. And there's the moment. I've hit it. 131,072 bacteria. Good to go. Next, how many bacteria after 200 hours? Holy smokes, if 17 was this big, 200 hours is going to be insane. I'm kind of scared, actually. Okay, let's do her, though. 200. First of all, 200 is off my X scale, so I'm going to make my X scale at least 200 so I can see it. Let's go 300. Way over here, this is going to be monster. Monster! Okay, I'm tired. Okay, here we go. Now, I gotta make this huge, huge. So let's go like million. 1, 2, 3, 4, 5, 6. Is that enough? Not even close. Let's keep adding zeros. Wish this was my bank account. 1, 2, 3. Boom, 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 boom. Just keep adding zeros. I can kind of see it there. So I just kept adding zeros till I hit it. And then where is that actually hitting? Holy Toledo. If there was that many bacteria, I think we'd be dead. So it's the Y value is 1.60694 times 10 to the 60th power bacteria. That's more bacteria than there are atoms in the world. Insane. But I could find it. Desmos to the rescue. Just had to change my window. Okay, now because that's such a awkward moment, I'm going to go back here, change this back to my happy place of like 12 hours and make this back to 3,000-ish. Uh-oh. Okay, let's go back home. There we go. Back home, make this 3,000. Make this at least 12. What's going on? 12. Make this -1. -4. There, better window. Now I can answer my last question. Calculate the time it would take to have 650 bacteria. Bacteria is Y. So get rid of this mess. Y equals 650. Again, type it in properly, McPhee. There we go. And the window's already set up. Click. The point is 9.3443, comma 650. Answer it appropriately. What does this represent? 9.344 hours is when we will have 650 bacteria. Okay, I am going to leave it at that because I think that lesson is more than sufficient in the sense of things. So what I'm going to get you to do is work on this example, and I'm going to make that available in class to see, so you can see what this is. Go through the questions. I'll have the answers here. And then same thing with example number 4, because they're really the same stuff over again, just with predicting what it is. And then you've got these answers, or these questions that you can do. Now the trouble with the assignment, which I don't like, there's no meaning to these. Like there's no hours and time, which I don't like. I like to fix that in the future. But that's all we have at the moment. So there's 5 examples here, and then it jumps to another set of same thing, about 10 of those, and then there's an answer key on the back page. So there's 15 of these to kind of practice. If you do those, you're more than good. And in the answer key, they'll give the equation, and then they'll have an E here, which just means extrapolation. An I will mean interpolation. Anything with NA would mean it doesn't exist. I think you're good to go. Okay, have fun. Put the des in Desmos. Whatever that means, I do not know. All right, have fun.